All right, section 10.7. It's actually going to look very, very familiar. Some parts of it's going to look very familiar to what we did yesterday as far as secants intersecting inside the circle and all that kind of stuff. But the big difference today that we didn't talk about yesterday is we're going to talk about the lengths of the segments, not the arcs, right? Not the measure of the arcs, not the measure of the angles. We're actually going to talk about the length of the segments themselves, right? So what I'm going to do is I'm going to put two tangents here. Just put them any old way. Let's just say like that. All right. There's not two tangents. They're not tangents. What are they? Secants. They're two secants. Right now, technically, secants keep on going. Right. They're lines. But what we're doing is we're just stopping from one point of the circle to the other. Okay. So we're taking a segment of the secant. You with me on that? All right. So let's do this. I like to do it a little bit differently than the way they do it. What I'm looking at here is I'm looking at the lengths of these segments, not looking at the angles and the arcs. We already talked about that yesterday. What I'm doing is I'm looking at the lengths, how long these segments are. So if I put a little A right there, what does that represent?
How long
From the circle to where? Where they intersect. Okay, so that's the length of A. I'm going to put B right here, and I'll tell you what, just to make it a little different, put C here and then D right there. Everybody okay with that so far? So this represents the length of A, this is the length of B, C, and D. Now I'm not going to go through any proof or even try to explain, this is how they came up with this, because I really don't know, to tell you the truth. I'd have to sit down and look at it and decide how they came up with this. I don't even know if I could do that on my own. But I will tell you what they came up with. Whoever came up with this is what they came up with. Now notice, this A and this D are not necessarily equal to each other. This A and the C are not necessarily equal to each other. The lengths of both of the secants are not necessarily equal to each other. All right, so I'm not making any assumptions about any of that kind of stuff. All right, but they do intersect, and they intersect where? Inside the circle. Okay, that's a big important part to this. There are two secants that intersect inside the circle. The segments that are formed by that point of intersection, watch. If I take A and multiply it by B. I'm multiplying them together. It's AB. It's not A plus B. It's A times B. That's going to equal, what do you think? If I take A times B, you're exactly right, C times D. That's kind of cool how that works out. All right. I don't know how they figured that out or how they would prove it, but that is one of our theorems. There it is right there. It's pretty wordy. If you look at this, actually that one's not so wordy. There's another one that I'm thinking of that's kind of wordy. The next two, but you can look at it, you can read it. This is how I like to write it. They write it a little bit different because they make this like capital A, capital B, and a C in the middle, and then they say this is like AC and BC. I just think this is a little bit more compact, a little bit more clean. I just kind of like it like this. It's always true. Anytime you have two secants that intersect inside a circle, these two are equal. Now look, I can't take A times C, can I? Because they're parts of different secants. But I can take the two parts of this one secant, multiply them together, and that's going to equal the two parts of the other secant multiplied together. Yep.
What if you have one really long one that goes down the middle?
Doesn't make any difference. As long as they intersect inside.
A tiny one at the bottom?
Yep. Doesn't matter.
So how would they equal if they're different sizes?
Their products would equal. So it doesn't make any difference. So you're saying if I have one like this,
yeah, right?
And then I have one like this.
Yeah.
Yep.
Oh my God,
well, because look, this is big, right? But that's extra small, isn't it? And neither one of these are like extra small. I don't know. We could do this. We could put it like that. It's still going to work. I don't know how. It does. All right? Because this is quite a bit longer than this one, right? I think it has to do with ratios and all that kind of stuff. All right. Again, I don't think I've ever seen a proof on it. I don't know if they ask you for a proof on it. They don't show one in the example. So if they don't usually show one in the book, it's usually a little bit tough, the proof. So I've never seen it. I mean, if you wanted to look for a proof, you could. But it's still going to work. All right. It's still going to work. You got it? Okay. Let's do an example with that situation. All right. Let's see which one do I want to do. Do we have time? Yeah, we got time. Let's do 2 of them. All right. Looks like that goes about like that. About right there, and then this goes here. It doesn't have to be exact, doesn't have to be to scale, as long as we just know what our numbers are. This is x, and this is 10, and this is 5 and 12. So that's 5, and that's 12. All right. So watch what we're gonna do. You watching? Everybody watching? Come on. So how are we gonna set this thing up? Yeah, 10 times x, which is just 10x, right? Equals what? 5 times 12, which is 60. I'll tell you what, just since I'm teaching this, I'm going to write 5 times 12, just so if you look back on it, you'll understand where I got the 60 from. Is that all right? So 10x equals 60, x equals 6. All right? And there it is. Very easy. Yeah. So x is 6. Everything's what? Has a special something? Yeah, there's a lot. You think this is special?
It's not
Is it?
special.
It's pretty special, I guess. 2 secants that intersect inside the circle, then you know the product of the segments are equal to each other.
This stuff
All right?
changes in grammar.
You have like 5 bell skippers scattered.
Well, they have to intersect each other,
Yeah,
1, 2.
but they would be 2 secants. They would be considered 2 secants because the chords, right? What'd you say? I have a lot of bell schedules in here. Yeah, you wouldn't believe how many times people say, "What time do you get out today?" I was like, "Well, look at 5 different places in my room, and it'll tell you where we get out." All right, let's do another one. This is not much more difficult.
1, 2, 3, 4, 5, 6, 7,
This is not much more difficult, but I don't
9,
know.
10.
For some people, it's a little challenging. What are you looking at?
You have like 10 bells.
Well, I counted 2 of them.
Well, one's Wednesday, one's regular, so I don't count those.
Sorry.
I count them all as one. Let's see, what am I looking for? Okay, this is x plus 1. That length right there. This is x plus 8. This one's x plus 10. And this is x. Alright, there you go, and it says solve for x. What do you think?
No. You just do 2x plus 10.
Why don't you do it? I'll give you a second to do it.
Fine.
Okay, that's enough time. So let's do this. You could do either one. It doesn't matter which one you start. I'm going to do this one right here. So you multiply those together, take the product of those, set it equal to the product of these. Now look, parentheses are very important here, aren't they?
Yeah,
Did you put parentheses around them?
I did.
Yeah, because if you're multiplying a sum, all right, you must put it in parentheses. You follow me? So let's do a little distributive property. We'll do this real quick. And you guys were right. You said FOIL on this, so that's what we do. So it's x squared plus 8x plus 1x. What's plus 8x plus 1x? Plus 9x. Okay, plus what? 8. Look what we can do. Look what happens to the x squareds. This is real nice and easy. Subtract an x squared from both sides, right? So they go away. Let's do this. Subtract a 9x from both sides. That's an x equals 8. There you go. That's your answer. So if you wanted to, you could fill in some other stuff. They might not just ask you to solve for x. They might ask you to find the lengths of the segments or something. So what's the length of this whole segment right here then? Well, this is 18, right? And this is 8, so that whole thing's 26. Right? That segment right there, that tangent. What's this going to be? Well, 8 plus 1, that's 9. And that's 16, so what's that? It's 25. Remember I said that the two segments don't necessarily have to be equal to each other, and they're not equal to each other, are they, in this case? Now, there could be situations where they were equal, right? But not in this situation. Easy enough, right?
Yep.
Hardest thing was just do a little FOIL method. You remember that from Algebra 1, don't you?
Yes, spelled wrong.
Okay. Spelled FOIL wrong?
Yep.
Yeah, well, if you learn FOIL method and then spell it incorrectly, yeah, you're going to have a little trouble. All right, let's do another one. Ready? It's just, what do you call it? Distributive property.
Do you?
Right. No, you could, as long as you do the first, right, as long as,
I would do first.
right. So everybody says inner, outer. I never said that. I always say outside, inside.
Cool. I always spell it like I-O.
Okay, here we go. Watch this. Here's two secants, but these two secants don't meet inside the circle. Take a wild guess.
Outside.
Right. they intersect outside the circle.
Now that's whack.
Now look, it looks exactly like what we did yesterday, doesn't it? Because remember what we talked about yesterday? We talked about the angle and the arcs. But today we're not talking about the angle and the arcs. What are we talking about? The lengths of the segments, right? Okay, so let's do this. This has some similarity to what we have been talking about. Let's call that A, call that B, call that C, and D. Everybody with me? Now, here's the deal. Again, I don't know the proof on this or anything like that. Just trust us, I guess. All right. So look what we're going to do. I'm going to say this a little bit differently. If you look at how they write it in the book, it's very, very word intensive. Okay. But I'm going to try to make it as easy as I can for you. Look what you have. You see this A segment? This is outside the circle. It's called the exterior segment. B is inside the circle. It's the interior. I'll just say outside, inside. Okay. So we got the outside, which is A. We got the inside, which is B. Then you have the outside, which is C, and the inside, which is D. All right, on that secant. Here's our theorem. We don't just go A times B equals C times D, because that would be the same thing as if they intersected inside the circle. But it's different. Okay, it's different when they intersect outside the circle right here. Here's what it is. It's A times, listen to what I say, it's the outside times the whole thing. What's the whole thing? People say that all the time. It's A plus B. It's not AB. AB is A times B. Because look, if this was 3 and then this was 2, you don't say 3 times 2, which is 6, do you? You say 3 plus 2, which is 5. Does that make sense? Okay, so it's not AB, it's A plus B. So now notice what I just said. We take the outside, right, and multiply it by the whole thing. That's just a little easier to remember than reading all the words that are in that theorem. Okay, so I take the outside times the whole thing. What do you think that's going to equal over here? If I take the outside times the whole thing, that's right. So I take the outside times the whole thing here. C plus D, exactly right. That's your theorem. When do you use this? You use it when you have two secants that intersect outside the circle. If you have that situation, it's broken up into these segments, then that works real nice and pretty. Let's do an example, okay? Everybody got that down? Okay. So let's see a good one. Let's make the secants go in the other direction this time. Alright, so let's go right there is one secant, and let's say go across like that's another secant. And let's say that this little bit right here is x. This one's 8. This one is 6, and this one is 10. Alright, so here we go. You ready? Paying attention? So what do we do? It's the outside times what? The whole thing. So let's do the top one. So what's the outside? 8 times the whole thing. What's the whole thing? X plus 8 equals the whole thing. I'm sorry. Let's go outside the whole thing. Outside is 6 times the whole thing, which is what?
16.
Yeah, we'll just put a 16. Everybody understand how we got 16, right? 10 plus 6. Okay, good. Now we just solve for x and we're done. It's as easy as that. Algebra is simple. So it's 8x plus what? 64. What's that? 96, is that right? I think it is, right? Yep, 36 add a 9, or a 3 to the 6, right. Okay, subtract 64 from both sides. And 8x equals, what's that, 32. Divide by 8, x is 4. So there you go, x is 4. They could ask you the length of the whole thing, couldn't they?
Yep.
Alright, that would be easy enough. So if that's 4, this whole thing is 12. Easy enough. It's not so hard, is it?
Nope.
Nope. Alright. I don't think... Well, at least the examples they give you here aren't really any more difficult than that. Yeah, we'll just keep it like that. That's good enough. Let's move on. We have one more theorem to do. Now look, we did two secants that intersect. Listen to me, don't talk. We have two secants that intersect inside the circle. We have two secants that intersect what? Outside the circle. So now what we're going to do is we're going to have a tangent and a secant. That's right. That's what we did yesterday, isn't it?
Yes.
Did we do a tangent and a secant yesterday? Yeah. So we're going to do a tangent and a secant today. Point outside the circle, all right? Follow me? So the tangent would hit about right there. And the secant, we'll just have it go through here like this. And, I don't know, what haven't I used lately? Orange. So watch, we'll call that A, we'll call that B, we'll call that C. This is very, very close to the thing with the two secants intersecting outside the circle. Let's start with this part right here, because that's a secant, right? And it intersects outside the circle. So let's set that up. How did we set up the last one? We went the outside times the whole thing, right? So what's the outside? To this bottom secant right here. What's the outside segment? It's B times the whole thing, which is what? B plus C. That's going to equal, now look at this. This is a tangent, right? Hits right at that circle right there. Look at the outside segment. Well, the outside segment is the whole entire thing, isn't it? All right? So if I go the outside times the whole thing, what do you think this is going to be? You got it. It's going to be a squared, isn't it?
Excuse
Allie,
the
is that what you're
interruption.
gonna say?
I have some announcements regarding today's athletic events.
All right, so what were we talking about here? So if look at this. Up here. Okay. No matter. Up here. Watch. This whole outside times the whole thing. So what is it? It's A times A, which is A squared. All right, so that's our little formula right there. So you take the tangent and you square it, and it's equal to the outside segment of the secant, right, times the entire secant. Make sense? It's not so bad, is it? It's very similar to that other one, isn't it? Yep. I think so. Well, let's do an example, okay? We got time. It's always nice to do an example with these. Let me find a nice... Oh, you're going to love the math on this.
Why?
Is it easy? Or why was it
I'll tell you, let's just keep it there. All right.
Well,
Let's
this
do
is
that.
not example for
Let's draw that. Let's draw this like this. All right, we got some time. I'm going to go through it. So watch this. This is 8. This is 7. And this is x. All right, let's set the thing up first, and then we'll worry about the math. So what do you want to do? I always like to do the one with the x first, okay? So we take the outside times the whole thing. What's the whole thing? It's x plus 7 equals what? The tangent squared, right? So it's 8 squared. So look what I get. I get x squared plus 7x equals 64. Now, that was all the geometry. Now it's all just algebra. All right? This is good for you. Did you guys learn quadratic formula?
Yeah.
Okay. So if you knew quadratic formula, it shouldn't be a problem. What we do in order to use quadratic formula, we have to have this thing set equal to 0. So let's get the 64 over on the left-hand side. We do that very easily by subtracting a 64, and we just set that equal to 0. Now we're ready to use the quadratic formula. Now you could give it a shot and see if it factors if you want to. Do you remember doing factoring in Algebra 1? Okay, so you could give it a shot, but I'll give you a hint. This does not factor. All right, so we need another way to do it. In Algebra 2, you're going to learn another way to do it. It's called completing the square. All right, you could complete the square if you wanted to, but let's use the quadratic formula. That's always lots of fun. So watch, x equals, here it is. Now, I'm not going to have you memorize this in this class, not in geometry, but when you get to Algebra 2, you definitely should have this memorized. All right, so it's square root b squared minus 4ac, and it's over 2a. Now, what's up with the a, the b, and the c? Well, watch. Here's the quadratic equation. In Algebra 2, this is one of my favorite things to do in Algebra 2, is to take this, we use completing the square, and we actually do a whole bunch of work, and we actually solve for x, and we come up with this as our solution for x. Isn't that crazy? From this thing right here. So what is the a? Well, the a is the thing that's being multiplied by the x squared. What is the b? The thing that's being multiplied by the x. What is the c? That's our constant. That's just the number that's sitting there by itself. So in this situation, what's our a, our b, and our c?
We have 1.
It's 1, 7, and negative 64. So all it is just plug and chug once you know the formula. Right? So plug some stuff in. So x equals negative b. This means the opposite of b. That would be what? Negative 7. Plus or minus. So what we're doing is we're actually combining two things. We're combining negative b plus all this stuff over 2a, and then it's also negative b what? Minus. But we just combine it into one nice little simple thing. So right now I'm just going to put negative 7 plus or minus square root of b squared. What's our b? 7 squared is 49. Minus 4 times a, which is 1, times c, which is negative 64. And that's all over, what? 2 times 1, which is just 2. So let's just simplify this. It's not that hard. It's just basic arithmetic, to tell you the truth. What is this? Minus a negative. What's minus a negative going to give you? It's going to give you a plus, isn't it? So what's 64 times 4? 120. 256. So 256 plus 49. 256, 49. That's a 15. That's a 10, 0, 305. Is that what you said? Good. All right, 305 over 2. Now what do we do with this? Chuck it in our calculator. Okay, that's what we do. Because they have a decimal answer here. All right, let's try this again. So watch. There's two parts to this. There's negative 7 plus the square root of 305 over 2. That's one answer. And then you go negative 7, what do you think? Minus square root of 305 over 2. So let's do this. So it's negative 7 plus the square root of 305. Oh, you know what I should have done? Well, let's do this. Let's hit equals. I should have put parentheses at the beginning of this negative 7, and then watch what I can do. I can just take this answer and then take the and divide it by 2. I think that'll work. Yep. 5.2. Yep. So that comes out to 5.2. Is that all? Is that our only answer? No. We also have to do the minus part as well. So let's do the same thing, but do minus instead of plus. So it's negative 7 minus the square root of 305. Okay, and that equals that. See, that's a negative, isn't it? And then what do we do with that? Divide that by 2, right? So take this answer, right, and divide it by 2, and we get negative 12.2. So x is negative 12.2. Now look, if this was algebra class, we would circle them both and we'd be done. But this is not algebra. We're actually finding something specific. What are we trying to find? We're trying to find the length of a segment, aren't we? Alright, so lengths of segments, can they be two different lengths? The same segment be two different numbers? No. So what do? How do I know which one works? Take out the negative one. That's right, because a length of a line segment cannot be negative anything, can it?
Why do we do that?
So, because it's a solution to our problem, but it's not going to give you a length. Right? If I took that negative 12.2 and plugged it back into our little equation right here, it would work. It would make this thing work. Right? But it's not gonna get you the value of a length. It's not gonna give you the length of anything because it's a negative. You can't have a negative length. So that's your answer right there, and then you would be done. 5.2.
Wow.
Okay? So aren't you glad you did that?
No.
You will be glad next year because you'll want a little bit of familiarity with this because you'll do a ton of this in Algebra 2. Am I right, David? You've done a lot of this. You're in Algebra 2 now, right? I thought you were. I thought you'd taken both. But you're not taking both? Not right now, this minute. I'm talking about this year. You're taking Algebra 2 as well, aren't you? Just the girls are? Okay. But Josh is taking it, but he's not doing geometry. So who's doing both? Just all the girls are taking both? Oh, just Joanna and Leah? So the other, and Jane. So Hannah's not doing it. Okay. All right, anyway. Well, anyway, I thought you were taking Algebra 2. You've seen this before, haven't you?
Yeah.
You saw that at home, didn't you? Okay. All right, that's it. Oh, let me give you some problems to do. I don't want to forget that, do I? Section 10.7. Oh, good.
I'm not going.
Where did I put my
I'll give
book?
you
Here.
her number. 358-163.
Well, you got like an hour drive. Do it on the way down.
With the way this
That'd be
all
fun.
drives, it doesn't take an hour.
10.7. Let's see. Page 740. And we're doing 6 to 21. There it is. Enjoy. Good luck in Math League tonight.